this look at our Zoom classes. So let's begin with the angle between, can everybody see the book? The angle between a line and a plane. We've kind of mentioned this in the last class because it's a bit related to this distance that we proved. Remember when we proved this last time? The idea kind of relate to it. We drew a line here, then we establish an angle here, something like that. Now, the only difference is the angle that we used to establish the distance D in the previous proof that we did together is the angle between the line and the normal to the plane. Are you with me? Okay, but this time around, we need the angle between the line and the plane. But both of them are kind of related, okay? So just similarly, just like we have done before, cos of this angle, because this is the angle between a normal and a plane, in terms of what's it called now? Let me find. We've had in the past, we've talked about angle between two vectors. If you have this vector and this vector, they must, originate from the same area. Then this angle is connected because this is acute. So we can say this is equal to, remember this? And we're able to establish that cosine of the angle is actually the absolute value of A dot B divided by absolute value of A and absolute value of B. Okay, we've had that before. Then yesterday, or was it yesterday or the day before, I don't know when we had that, we were able to prove that our D is equal to something, and along the line, we established something similar to this. So let me go back to that book. Okay, cosine of this angle is this. Okay, is the cosine of this angle, actually we don't even need to think of it that way. We can think of it the same way. This line represents a vector, which is the normal. This represents another vector, okay, in the direction vector of the line, as D. Now, direction vector of the line may not necessarily be the line, right? Okay, it may not necessarily be the line. However, we can use direction vector. Angle between the direction vector of a line and another line is actually the angle between the two lines. I don't know if everybody gets what I mean. I'll go back here and show you what I mean. If you have a line, then this is the direction vector. Yes? So if you are looking for the angle between these two lines, is actually the angle between the direction vector and the line as well. Or the angle between the two direction vectors, because this we have a direction vector also. So it's actually the same as the angle between the two direction vectors. Does that make sense? So this is the whole idea. So in this case now, the line, the first one, maybe I should use partly my textbook so I don't have to go back to a different screen. If you have your textbook also, you may refer to it, but no need, just concentrate more. In this case, we have a normal, which is quite easy to get when given the equation of a plane. Yes, we have the normal. Then we have the line in question with direction vector D. So we just assume D is the direction vector of the line, yes? So the line may actually not be this. Okay, this may not be the line, but of course, finding the angle between the line and something is finding the angle between the direction vector of the line and something. Is that clear to everyone? Okay, because the direction vector of the line is easy. Remember, that is that coefficient of t, okay, in the vector equation of the line. So that's easy to pick. Also for the normal, that is easy to pick. Okay, and once we do that, the angle in question here is the angle between them, which has been established to be this one. Okay, not this one. I'll tell you how this one comes in now, for those that do not see it immediately. not this one, just this one. So basically, let's go back. Where is it? Okay, so again, I have a plane. There is a normal to the plane, and there's a line somewhere, but this is the direction vector of the line to the plane. Okay, now we're interested in this angle because it's easy for us to establish first. Okay, now this is the normal to the plane, this is D. So the angle between both of them simply is connected to n dot D is equal to absolute value of n, absolute value of D cos theta. Yes? And then cos theta is simply absolute value of n dot D divided by absolute value of n and absolute value of D. We know that. However, this is easy to establish, but this is actually what we're interested in. Let's say phi. Okay? There is a connection. Phi and theta is connected by what? What is the relation between phi and theta? Anyone? This is phi and this is theta. Karen, can you guess? Or can you tell me? Sorry, not guess, you should know. What is the relation between phi and theta?
Like sine phi equals cos theta.
Why?
Sorry, what did you say?
Why? Why is the sine of one equals to cos of the other? If you know the connection in terms of in a right angle triangle, how are they related? Okay, then you can prove, you can explain why the sine of one is equal to the cos of the other. I don't just want you to memorize that sine of one is cos to the or cos of the other. Do you know? Say that again.
Because they add up to be 90 degrees.
Thank you. So phi plus theta actually add up to be 90. So what do we call such angle, anyone? Vena?
I can't remember.
It begins with a C. Try. Begins with a C. Nakita. Any idea? Angles that add up to 90.
Still thinking.
Let's try Clarissa. It's some simple word you probably just forgot.
Complementary.
Complementary. Okay, so these are complementary angles. So we are using elementary trigonometry here. Okay, complementary angles. Please forgive my rubbish. I don't want to write too much stuff. I'm just trying to scribble stuff while explaining. All right, then you can form your notes better yourself. Complementary angles, yes. And if we have complementary angles, we already know that the sine of one is cosine of the other, isn't it? During our elementary trig. Okay, if we have complementary angles like 50 and 40, sine of this will always be the cosine of that, and vice versa. Does everybody get that? And the reason is because in the right angle triangle, if you have here phi and you have here theta, okay, and this is maybe A, B, C, you would realize that sine of this is B over A, and that is the cosine of this one, which is also B over A. Can you, do you understand that? Or maybe, I hope you can see my cursor. Okay, so sine of this one will be opposite over hypotenuse, that's B over A, which is the cosine of this one, which is also B over A. Okay, so when two angles are complementary, sine of one is the cosine of the other. And that is the reason for this. So a lot of things were skipped, which is why I thought I explained that. Okay, so actually the first established thing, if you are writing your note, is this one, is this. Okay, we already know Or do you want me to write it formally, or you can just pick it yourself when taking note of important points? Talk to me, guys. Can you form something yourself in detail, well-structured explanation for yourself? Okay. So we already know. So I'm going to, the way I will have written it, okay? We know that the angle between two vectors, N and D. Why are we using angle between these two vectors? To find the angle, so this is me starting over, and you can watch the video if you want to put it down in a better way. So please draw something like this. To find the angle between the line and the plane, okay, is the same as finding the angle between the line, between the direction vector of the line and the plane. Does that make sense? So if we let the direction vector of the line be D and the normal to the plane be N, then we can form the right angle triangle we can see, where theta is the angle between the normal to the plane, and is the angle between the normal to the plane and the direction vector D of the line. Does that make sense? Having said that, by previously established relation, cosine of theta is this relation, absolute value of their dot product divided by the product of their individual absolute values. Does that make sense? Okay. Then if we let phi be the angle between the direction vector of the line and the plane, which by extension is the angle between the line and the plane. Does that make sense? Then we could see that phi and theta are complementary angles. Okay, which means the cosine of theta will be the sine of phi. So as a result, the relation should be sine theta is equal to this. Okay, that is when we can get rid of this cosine. We can't start from theta. Okay, we cannot start from phi. We have to start from theta because we are making use of something that we have known before. Then we can now link it to where sine phi comes in. Am I making things clearer, or am I mixing things up? Is it clear, or is it just more confusion?
It's clear.
Clear. Okay, thank you. So the final relation will be sine theta is equal to this fraction. Then sine phi. Apologies, sine phi. Then phi will be the arc sine of that, and the phi will always be an acute angle, as you can see here. Okay, to always be an acute angle, as you can see here. And that is how we establish it. So let's look at this example. It's just going to be substitution. So it's not something that's, so let's look at this one. Can everybody see the blue screen? Okay, so just listen to the simple example.
We have already seen how to use the scalar product to calculate the angle between two lines. How can we use this principle to calculate the angle between a line and a plane? There are infinitely many vectors with different directions, but which are parallel to the plane. If we were to use one of these to calculate the angle between the line and the plane, we would first need to work out which one to use. By contrast, a normal to the plane has a unique direction. If theta is the angle between the line and the normal to the plane, then we can write an expression for cosine theta. Since the normal is perpendicular to any vector in the plane, we can construct a right-angled triangle as shown. If phi is the angle between the line and the plane, then sine phi must equal cosine theta. We take the inverse sign to find phi. In this example, the equation of the plane is given in Cartesian form, so the coefficients of the variables tell us the normal vector. The line is given as parametric equations, so the coefficients of the parameter are the components of the direction vector. We now use these vectors in the formula. The scalar product is the product of the x components plus the product of the y components plus the product of the z components. The length of each of the vectors is the square root of the sum of the squares of the components. We perform the calculations and recognize that the acute angle with sine 1/2 is 30 degrees. So, the angle between the line and the plane is 30 degrees.
Any questions? So, this screenshot will be sent. I want us to maybe practice something on that first. So, let's look at question 1 together. Do you need me to send? Let's send this first, so we can have an organized note. So I'll send a screenshot of this first now, but you don't have to write any notes now, please, because of our time. Then this is the example. So after this, let's look at question 1. So I want you to try question 1A and question 1A and 1D. Begin, please. 1A and 1D. So I've sent to your WeChat. Okay, so now for angle between two planes, as we have seen before, so if I'm looking for the angle between these two planes, each of the plane we have normal N1 and N2. So basically, let N1 and N2 be the normals to the two planes. Do I have everyone's attention, please? Yes, good. Okay, thank you. So let N1 and N2 be the normals to the two planes. So if you look at it from this angle, let's see, I haven't opened any of my 3D app today. I'm going to pick two planes. All right, on this 3D. Can you see my 3D app? Okay, so let me put two planes. Where is the first one? I'm just using my 5A, question 5A. 2x minus y plus z is equal to, I want to make sure everybody gets this. Then the second plane, x plus 3y. Karen, I'm about to ask you the normal vector, so please be ready to give me the answer. So these are two planes, okay? These are two planes. Can everybody see that? Now, Karen, for the first plane, give me the normal vector to that plane.
2, negative 1, 1.
2, negative 1,
1.
1. So you can see that is the normal to this plane. You can see that it's perpendicular to the plane. The normal is always perpendicular to the plane, isn't it? Okay. Then for the second one, Karen, could you give me the normal to that plane?
1, 3, 2.
1, yes, 1, 3, 2. Good. So you can see this is the normal to the other plane. Okay, so clearly now, this is the picture you are looking at in the book. If you want to find the angle between these two planes, which is this, can you see my cursor? Which is this angle. So let's see, this is the book. So these are the two planes. These are the normals to the plane. So these are the two planes, green and blue, like this. Yes, this is the acute angle between them. And we can see that it's actually the same as this angle. How? Let's come back here. To find the angle between these two planes, like this. Yes. To find the angle here, we are saying that is the same here. Why? Because if this angle is theta, and this angle is 180 minus theta, the sum of the angle in this quadrilateral we can see is 360. Yes? Now we already know the angle between the normal, each normal and each plane to be 90. Can you see that? Between here and here is 90. So out of the 360, two angles already took away 180. Understand? Which means the other two angles are what to each other? Anyone? Lillian, not you yet. Let's start with Werner. My question is this. This is a quadrilateral, yes? Now, this is perpendicular because a normal is perpendicular to the plane. This is also perpendicular. A normal is perpendicular to the plane. Out of 360, these two already share 180, which is half of it. How these guys decide to share the remaining 180, we don't care. But we know that the addition will be 180. In that case, we can say this angle and this angle are what to each other?
Is it correspondent?
Close. It begins with a C also. No, actually, it doesn't begin with a C. My apologies. That was a complementary. Nakita, you want to try? S is the first word.
What?
S is the first word.
Metric?
S is the first word. S for science.
Yeah, isn't it symmetrical?
No. Symmetrical is when you can visualize something in halves. Vena, you want to try again?
Supplementary.
Supplementary. Supplementary angles are angles that add up to 180, isn't it? Complementary for 90, supplementary for 180. And I've told you how I memorized this in quotes when I was growing up. I arranged the letters in alphabetical order. I arranged the numbers in the order of their magnitude. So C comes first, 90 comes first. S is the second, 180 is the second. That's how I learned it because my grammar was terrible back then. So I had to look for a pattern to memorize some stuff, okay, to avoid being mixed up. So if you want to think about it that way, okay. So if these two are supplementary angles, clearly, if this is 180 minus theta, then this must be, if this is 180 minus theta, this must be theta. Understand? Raise your hand if you understand what I mean. Okay, thank you. So the angle we're actually looking for, theta here, is actually the angle between the two normals. That's the point here. So, and it's easier. So it's in this picture. I've sent this picture to you. I just wanted to show you in the 3D plot. And it is easier to get the normal vectors. So we don't have to be concerned with the whole thing anymore. Okay, so we just find the angle between the two normal vectors, which is like finding angle between two vectors. And we already have a relationship in terms of their dot products. So we are using this again. So again, the angle between a line and a plane, we use sine for that reason you have seen. For the angle between two planes, you consider cosine, which is actually the cosine connecting the two normals to the two planes. And the reason we are using that is not because we want to just memorize something It's not because we just want to accept, oh, that is how it is. We can see already. That is why I show you in the three-dimensional plot. And if you move this plot around, you can see clearly how that thing was formulated. This one is exactly what you have here. It's like you looking at it from one, it's the cross section, if I may use that word. Does it make sense? Okay, so with this, you can practice the next. So there are two things that we have learned now in the angle in space. When you're in a space, you might be interested in angle between, actually angle between two lines also, yes, but we have done that in the past, so we don't need to bother. An angle between two lines does not have to be classified under space because a line could be in a plane as well, okay? But if we are talking about space, we want to see the angle between a line and a plane, or maybe the angle between two planes, and that's it. Understand? And this concludes the part H. So for those that are done with number 2B, please proceed to number 5A and E. I just picked the extreme 2, 5A and E. Then if you are done with that, then proceed to number 6, 5AE and number 6. Okay? So I'll send this to the notes. Oh, there's an example, but before I play the example, just in case we can learn one additional thing, I will play the example for us. So I'll send this to the group first. So here is the notes. And here is an example. I'll send a screenshot first, then I'll play it. It's possible you hear something in the explanation that might be useful. So that's why I'm going to play it. Okay. So I want everybody to be attentive. Let's play this. We might get one or two things from the explanation given by the self-tutor app. I want to be sure that I'm sharing my computer audio. Yes. So please give me this sign if you can hear the audio as I'm about to start now.
Consider two planes which intersect in space along a straight line. If we view the planes directly down the line of intersection, we can identify the acute angle theta between the planes. We can immediately mark the supplementary angle next to it. Now consider the normal vectors to the planes. Using the angle sum of a quadrilateral, the angle between the normal vectors must be theta. So, the acute angle between the normal vectors is also the angle between the planes. In this example, the planes are both given as Cartesian equations, so their normal vectors are the coefficients of x, y, and z. We now use these vectors in the formula. The scalar product is the product of the x components plus the product of the y components plus the product of the z components. The length of each of the vectors is the square root of the sum of the squares of the components. We perform the calculations and take the inverse cosine to find the angle between the planes is about 72.0 degrees.
Understand? So you may now proceed with the questions. So maybe I send all the questions now to you. I think I sent the first one before. I think I sent the first part. Let's check. Yeah, I only sent up to number 2. So now I'm going to send the entire exercise. Okay. You can always do the rest later. And if you need the solution, please let me know. So do questions 5, AD, and question 6 for this aspect. And later on your own, please do 8 later. Okay, it looks technical. Actually, 7 and 8 later. Looks technical. Let's make an attempt and see me if something is not clear. Did I say 5A and D? Should have been 5A and E, the last two. So edit that. Okay, updated version sent. So after that, you do question 6. Send 7. Send 8. 7. Yes. So please do not try 7 and 8 in class because of our time. Take your time to do it later and contact me if you need help. So just do 5AE and 6. They are direct, simple applications of what you have done, similar to question 1 and 2 that you did earlier. And please attend 3 and 4. So there are just 8 questions. Please spend some time to play with them. So the last part will begin maybe in about 10 or 20 minutes, depending on how long the other one takes you. Even if you do not complete it in class, please complete later and send to me. Ask for help, please, if you need any help. So I'll give you some time to work on your own. Pause the recording. We don't need to record any simple correction or observation needed. 2B says, let's share that book. 2B says, show that the line, right? 1 minute. Show that the line is parallel to the plane. Can you hear me, sir? To show that the line is parallel to the plane, all you have to do is to show that the angle between them is 0 or 180.
Mm-hmm. No, I get that part, but how do you do B?
B, oh, that is similar to what we did in class. If you want to find the distance between a line and a plane, the distance between a line and a plane, but we already know that they are parallel. Look at B, right? We already know they are parallel, isn't it?
Mm-hmm.
So to find the distance between a line and a plane, pick a point in one and find the distance to the other. And we already look at that, the formula for D that we established. Remember that formula? The formula to find the distance between a point in space and a plane, this one.
Oh, okay.
Okay. So this is a plane. P is any arbitrary point that is perpendicular, like that. In this case, your point will come from the line. Understand what I mean?
Yeah, okay. Thank you.
If your point, how do you make sure your point comes for the line? Can you tell me?
You can, from the line, you just substitute like any number into t, right?
Exactly. Substitute any number as t, get a point from the line, then use this formula, because your ABC will be what? What does this represent? The vector, isn't it? The normal vector, it's ABC, right? So you only need the normal vector of the plane, you only need the normal vector to the plane and the arbitrary point that you have picked, and you can use this D formula. That's it.
Yeah.
Okay. So if anyone else is struggling with that, I hope that explanation is clear. Yes? Okay, so if there's anything, please talk to me. Something koala, I forgot the first part. Something G, koala, we were taught a few days ago. I'm a bad student, I forgot. Anyone?
中秋节快乐，
What?
中秋节快乐，
John Jie.
秋 Yeah.
John Jie, koala.
Mm.
Is that right?
I think so.
What? Dude, you think we need to take away your Macau ID or passport or anything you have in Macau?
They probably should.
Is it? Okay. I wasn't sure if the John sounds twice, you know. Krista, come on, don't look at me like that. Teach me something. Okay, yeah. You see, I trust Krista. I knew she would do something about it. John Chi. Okay, is it Chi? How do you pronounce this? Q-I-U. Chiu.
Chiu,
Chiu. Is it Chiu? Come
chiu.
on. John Chi Jie or something. Quite a lot. Anyway, you understand. I'm wishing you happy. Thank you. All right. Back to work. Karen doesn't even care about my greetings. Thank you, Karen, for not caring about my greetings. You don't even know if I got it right or not. All right. So I'm looking at what you sent me now. Okay, so I'm putting question 6 in the 3D. Oh, depending on the value of K, but I will use the answer for the value of K that someone has done. So let's put this in the 3D plot. You may proceed. When I'm done, I'll tell you. Let's say share the 3D plot, okay? So I'm putting the question in 3D plot. The first one is X plus 5Y minus 3Z is equal to 8. And the second is 2X
Plus 2y.
2Y, thank you.
4, no, 4.
Very good. So 4Z, right? Because you got 4. Is it 4 or minus 4?
4.
4. All right. So clearly these two planes are perpendicular. You see, it's so obvious to see. It's like so easy to see that they're perpendicular. Okay, like that. Now, these are not their normals because this is the previous normal. So the normal vector would be 1, 5, yes, -3 as the first one. For the second, the normal will be 2, 2, 4, yes. And the normal vector doesn't have to be 2, 2, 4. It will also work with 1 like that too. The only difference is the length is different. So, Werner, this is what I'm trying to say. Look at this normal vector, 1, 1, 2. But from the equation, the normal vector is actually 2, 2, 4. It's just about the length. So if you are looking for distance, you know, it will be a bit different. Okay? It will be a bit different. So I think for simplicity, so look at this now. If I'm looking at this, what is it called now? The cross section. Is everybody looking at this? I'm looking at something that looks like a rectangle, right? So for these two planes to be perpendicular, their normals are also perpendicular. Okay? So to show that these two planes are perpendicular, it suffices to show that their normal vectors are perpendicular, which means the dot product of these two normal vectors is equal to 0. That would be a very good explanation and something to use, a good condition to use. Understand? Okay. So please proceed with your work. Message received, Mr. Chang. 5e. All right, I'm looking at it. Yes, that's correct, sir. That's correct. So you just have to find the normal first and make use of it. Perfect. So I'm going to start the last parts in a bit, maybe 2 more minutes. And the rest of us can take our time to do it later. Intersecting planes. Yeah, something came in from Ms. V. Aha. I will investigate while you have an issue. Or have you seen why you had issue?
Yeah, I don't know why I wrote root 16 earlier.
Oh. Yeah. You wrote 16 earlier?
Yeah, I don't know why I did that. I see it now.
Oh, let's see. Oh, for denominator, yeah. Right?
Yeah.
2 squared is 4. 4 again. Oh my God, and I didn't see that. I was wondering what's going on. Okay, so I guess we're good now. Nothing to worry about. We're good now. Okay, great. All right, so that makes sense. That makes so much sense. Because since we prove for any arbitrary point, I was thinking, how can that fail in a specific situation also? Okay, everyone, if I could have your attention so we can get through with the last part and maybe close the meeting in the next 15 or 30 minutes top if you practice here. So let's just quickly look at the last part. The last part is intersecting plane, and with that we can say bye-bye to vectors. Unfortunately, we finish October 1st instead of September ending. But anyway, the practice was necessary, if you agree with me. 2 planes in the space could be any of the following 3 arrangements: intersecting, parallel, or coincident. Do you agree that this is one of the, like the classification of lines as well? Lines in plane, lines in space. We look at it, or let's say even in 2D. Lines in 2D can intersect, they can be parallel, or they can be coincident. Okay, so 3 planes, however, have this. 3 planes in the space could have the following 8 arrangements. That's like 2 raised to power 3, I think. Anyway, we'll see. It could be all coincident, all the planes are together. It could be 2 coincident, 1 intersecting. Okay? It could be 2 coincident and 1 parallel to the other 2. Hello? Does everybody understand all this? Now, it could be 2 of them are parallel while the other is intersecting. And of course, if it intersects with one, it's going to intersect with the other because they are parallel. All the 3 could be parallel. All the 3 could meet at a point. All the 3 could meet at a common line. There's a difference between plane meeting at a point and plane meeting at a common line. Can you see the difference? If they meet at a point, they're going to come from different directions and only one point is common to them. But in this case, the orientation is like the same, so they have a common line of intersection. And in this case, it could be the line intersecting any 2 is parallel to the 3rd plane. So let's see, the line intersecting any 2. So look at this line here, and it's said to be parallel to this plane. The line intersecting this one is parallel to this plane. Can you see my cursor? And the line intersecting these 2, which is this line here, the line that extends here, is parallel to the 3rd plane. So the line intersecting any 2 could be parallel to the 3rd plane. Let's look at this demonstration. One thing I love about this book is they have like demonstration. So if we want all coincidence, these are 3 planes together. Let's let's see. If we want two coincident, is this better or this one? This one, okay. If we want two coincident and two parallel, so two are together somewhere here. Two are together here. Can you see that? Oh, you can't see?
Are you sharing another screen right now? We can only see the text part.
Yes. Uh-oh.
Yeah.
Sorry. Okay, I'll start again. Can you see now? Please speak
Yeah,
up
we can
next
see.
time. I thought you were following me. So in this case, three planes are together as one. So they are all coincident. So that is the meaning of P1 equals to P2 equals P3. Does that make sense? This is for two planes. If two planes are coincident and the other one is not, of course, when we have this, the other one is intersecting, definitely. We have this. So two are here. We can have two coincident again, but the third one is parallel to them. Can you see? The third is parallel to them. We can have two parallel and one intersecting. So the yellow and the red are parallel, while the other guy is, okay, maybe I use this color. Good. Can you see everyone? So we could also have, let's go back. We could also have two parallel, this is one we're showing. All three are parallel. This is definitely the format of building, like story building. All the three floors must be parallel, right? Otherwise, maybe you come up with something else, which is not a good structure. So our school, I believe, is designed like this, and every building anyway. Understand? Each level must be parallel, something like that. All three meet at a point. See? Not a line. So these three planes have a common point, not a common line. Let's see what the line one will look like. Look at this. Orientation is different. This is coming from maybe x-axis, coming from y-axis, coming from z-axis. The orientation is kind of different, the way you look at it. But here, if they meet at one line, actually you can see them all from one point, like this. And you can see it as just line if you get the exact point well. But you can't do that here. In any way you put it, all meet at one point, you can't. Can you see the difference now? You can't do that here. So there's a difference between meet at the point. So the third one, two will meet, and their common line, like this red line, is parallel to the line that is common to the green and the blue. Are you getting my point? The green line is parallel to the intersecting line of the blue and the red. And the blue line, the blue plane, sorry, is parallel to the intersecting line of the red and the green. Does this make sense? So these are all the 8 possibilities for a plane in 3D. Okay, for plane in 3D, all the 8 possibilities. Okay, now, sorry, I just closed my screen so I can share. You see, our elementary rule operation, which you did in topic 1, is what is needed here. So there's no need to beat about the bush or waste so much time. So I'm just going to play, I think 2 examples were done to remind you of the idea of elementary rule of operation and the interpretation. Okay, it's 1 example. Okay, actually 2 examples. Then there are 2 examples. I'll play the 2 together. Then I'll send the questions and I wish you the best. Understand? Okay, let's go with the first one. Tell me if you can see. Can you see the example, self-tutor? Okay.
We can only see the textbook.
You can only see the textbook?
Yeah.
I have a blue screen, not the textbook.
We can't see it.
Okay, minute, sorry. How about now? Okay, so let's look at this. Solve the system of linear equations. In each case, give a geometric interpretation of the system. Definitely, because it's a 3 by 3 equation, it's a plane. Each of them is a plane. Understand? If it is 2 by 2, it's just a line. Does that make sense now? Because a 3 by 3, so it has a 3 variable. When you have x, y, z, you are referring to a plane, not a line. But just x and y, or just y and z, or just x and z, then you're referring to a line. Understand? So basically, asking you to solve and give a geometric interpretation is asking you to tell us what is the relationship between the 3 planes. Does that make sense? So let's see.
The Cartesian form of the equation of a plane is a linear equation in the variables x, y, and z. To find the intersection between planes, we therefore need to solve a system of linear equations. If we consider 2 planes in space, then we have 2 equations in 3 unknowns. The system is underspecified, so it either has no solutions or infinitely many solutions. Geometrically, there are 3 possibilities. The planes may intersect in a line, so there are infinitely many solutions along the line, be parallel but not coincident, in which case there are no solutions, be coincident, in which case there are infinitely many solutions in a plane. If we consider 3 planes in space, then we have 3 equations in 3 unknowns. The system may have no solutions, 1 solution, or infinitely many solutions. Geometrically, there are 8 possibilities. You should notice that 4 cases correspond to no solutions. 1 case corresponds to a unique solution, and the remaining 3 cases correspond to infinitely many solutions. We can decide which relation.
Does this classification make sense? So your first point of call is try to solve it. Because when we did elementary row operation, we will solve the 3 by 3, then we will get stuck. We can either get one value, or you have to introduce a parameter because there will be infinitely many value, okay? Or there will be no solution at all. So these 3 were grouped in those forms. These 8 were grouped in those 3 categories. So I'll move it back a bit so you can get that part again.
Geometrically, there are 8 possibilities. You should notice that 4 cases correspond to no solutions. 1 case corresponds to a unique solution, and the remaining 3 cases correspond to infinitely many solutions. We can decide which relationship there is between the planes based on the row echelon form representation of the simultaneous equations. You may recall there were 7 forms we distinguished. We can immediately match the case for a unique solution. Consider the 3 forms for infinitely many solutions. The third of these forms has 2 rows with all zeros, so there are 2 parameters. The solution space is therefore a plane, and this form must correspond to 3 coincident planes. The other 2 forms for infinitely many solutions have 1 parameter. The solution space is therefore a line. Either form could correspond to either of the situations where the solution is a line. However, we should be able to recognize directly from the equations if 2 of the planes are coincident. Now consider the 3 forms for no solutions. The space is therefore a line. Either form could correspond to either
I'm going to ask you a question after this last part.
of the situations where the solution is a line. However, we should be able to recognize directly from the equations if two of the planes are coincident.
Now listen. This will give us infinitely many solutions, yes? And if all three, okay, this is for two, this two, okay, is for the intersecting. It's possible all the three are intersecting, or, well, all the three are intersecting by a line, at a line, or on a line as the case may be, but two are coincident. Even though these two are like this, are of these forms, how do we know to differentiate later? The voice the tutor just told you, we should be able to know if two lines are coincident or not, which means if you can distinguish this, then you can also separate it from this. The question now is, how do you know which one this is? Anyone, raise your hand, please. How do you know that two planes are coincident? Mr. Chang.
One of the lines, one of the equations of the planes are just going to be a multiple of another equation of the plane.
That's it. One of the equation, so if L3 is a multiple of L1, before solving, you can see already that, oh, L3 and L1 must be together, must be coincident. Okay, so that will distinguish between this and this one. Does this make sense, please? I just wanted to chip that in. Hello, does it make sense? Can you guys talk to me, please? So this is you going back to your row operation in chapter, let me see when we did row operation. Does anybody know? Under linear algebra, chapter 11 of your green textbook. And we did 11D, 261, page 261. We did something of such in page 261. And we talked about infinitely many solutions. I'll probably share that page with you again, so you can use that to recall the whole idea. Understand? Okay, so let's quickly listen to this.
Now consider the three forms for no solutions. The third of these forms has a row with all zeros, and another row with all zeros except the constant. This tells us the planes are all parallel, so there are two possible geometric interpretations. We should be able to recognize directly from the equations if two of the planes are coincident. Considering the other forms, either form could correspond to either of the remaining geometric interpretations. However, we should be able to recognize directly from the equations if two of the planes are parallel. Having been through all of these cases, we can see the other forms, either.
How do you know two planes are parallel? Because if we can get the parallel one, then this one is easy. Anyone? By looking at the equation of the plane, how do I know that these two planes are parallel?
They are multiples except for like the part on the right.
The value for D will be different, right? And the other coefficient of X, Y, Z will just be exact multiple of the other, which means their direction vector will be multiple of the other. Understand? So the direction vector of the plane will be multiple of the other, then the two planes are parallel. Okay? Or if you look at it, they are normal. I think because we are dealing with a plane, let's look at it from the normal. The normal to the two will be the same. except that maybe one is a scalar multiple of the other. That's it. Okay, so if you can separate this from that, then you know you are dealing with this. Now, one might ask, why do we classify this as no solution? By no solution, we mean the three planes do not meet. We're not concerned if two of them can meet. Okay, we will be talking about a solution if the three planes intersect. And clearly, not all three intersect in these two situations. Am I making sense, please? All right, quickly now. So
Form could correspond to either of the remaining geometric interpretations. However, we should be able to recognize directly from the equations if two of the planes are parallel. Having been through all of these cases, we consider the systems of equations in the example. For part A, we write the system in augmented matrix form using the array of coefficients of the variables, a vertical line for the equal signs, and the array of constants. We can see that we already have a 1 in the top left corner, so we concentrate on getting a triangle of zeros in the bottom left-hand corner. We start with getting zeros in the first column under the 1. Look at the coefficients of x in the first two rows. What row operation can we perform on row 2 to make the first element 0? We start with row 2, then subtract 2 times row 1 to generate the new row 2.
I hope everybody remember this row operation. If you don't, this is being recorded. Watch it, or you go to the YouTube playlist and watch the row operation to refresh the idea. Understand? And that is why practice is necessary. So if I were you, this chapter 13I, the question on 13I are 12 altogether. Practice at least 6, especially question 4 that has to do with geometric interpretation, and it has 6 questions on its own. Do practice. I will send all the screenshots to you if you do not have your book. Okay? Practice. Use this opportunity to practice. Thank you.
What row operation can we perform on row 3 to make the first element 0?
Anyone? What row operation can we perform to make this 0? Karen, let's start with you.
Minus row 1.
Say that again.
Minus row 1.
No, not just say minus row 1. What's minus row 1?
Row 3 minus row 1.
Yes, complete that. Row 3 minus
Start with row 3, then subtract row 1 to generate the new row 3. Row 2 now starts with a 0. We look to make the second element 1. We multiply row 2 by minus 1 over 5 to give us the new row 2. We need a complete triangle of zeros in the bottom left-hand corner. So, we need to perform another row operation on row 3. Row 2 has the first element 0, so this is the other row we need to use in our row operation. The lowest common multiple.
Can somebody tell me why we need to use this row and why can't we use this row? Why is this 0 significant? What would happen if we don't, Nakita? Clarissa?
So we can keep the 0 in row 3.
Nakita, does that make sense? The 0 here must be kept. Failure to use this row, by the time you start multiplying and subtracting, you won't maintain the 0 here. This 1 will probably give you something when you multiply, right? For example, if you are to use this, you're probably going to say maybe times minus 3 plus this one, isn't it? To make this 0. And in that case, this will become that minus 3. But we need this to become 0. So it's better to use a row that already has 0 at that position. Just want to, because I'll be asking some of these questions so you can remember what you did in Form 5. All right?
Of 5 and 4 is 20. So we start with 5 times row 3, then subtract 4 times row 2 to generate the new row 3. Row 3 now starts with 2 zeros. We look to make the third element 1. We multiply row 3 by -1 over 17 to give us the new row 3.
With this format, guys, what is the interpretation you think this question will result into? Quickly.
One unique solution.
There'll be one unique solution. Thank you, Mr. Chang. It means there's a common point of intersection. Okay, point, not line. Point of intersection. All right?
Row 3 now says 0x plus 0y plus z equals -1. So z equals -1. We use this value for z in row 2. 0z plus 1y minus 3 over 5 times the value of z we have just found equals 23 over 5. Subtracting 3 over 5 from both sides, we find y equals 4. We now use the values for both y and z in row 1. 1x plus 3 times the value of y we have just found minus the value of z we have just found equals 15. We solve to find x equals 2. So the system has a unique solution. X equals 2, y equals 4, and z equals -1. The system therefore represents 3 planes that meet at the single point 2, 4, -1. For part B, we write the system in augmented matrix form using the array of coefficients of the variables, a vertical line for the equals signs, and the array of constants. We can see there is a 2 in the top left corner. We make a 1 there by swapping rows 1 and 2. We next concentrate on getting a triangle of zeros in the bottom left-hand corner. Look at the coefficients of x in the first 2 rows. What row operation can we perform on row 2 to make the first element 0? We start with row 2, then subtract 2 times row 1 to generate the new row 2. What row operation can we perform on row 3 to make the first element 0? We start with row 3, then subtract 3 times row 1 to generate the new row 3. Row 2 now starts with a 0. We look to make the second element 1. We multiply row 2 by -1 over 3 to give us the new row 2. We need a complete triangle of zeros in the bottom left-hand corner. So we need to perform another row operation on row 3. Row 2 has the first element 0, so this is the other row we need to use in our row operation. We start with row 3, then subtract 2 times row 2 to generate the new row 3. We see a line of zeros, which means the system is consistent and there are infinitely many solutions. Row 2 now reads 0x plus 1y minus 1z equals -1/3. Since there are 2 variables in this equation, we need to make one of them a parameter. Suppose we let z be the parameter t, then substitute it into row 2. We add t to both sides, so y is the subject. We now substitute for both y and z in row 1. We find that the t's cancel, and we add 1/3 to both sides. We then solve for x. In this case, x takes the value 7 over 3 no matter what value the parameter takes. We can now write the set of infinitely many solutions as the value of x and equations for y and z in terms of the parameter t. From the original equations, we can see the normal vectors are different for each plane, and none is a scalar multiple of another. So, no two planes can be coincident. We therefore conclude that we have three distinct planes that intersect in a line.
Does that last part make sense? Let's play that last part again.
Solutions. Rho equals minus. We find that the third to both sides. We then solve for x. In this case, x takes the value 7 over 3 no matter what value the parameter takes. We can now write the set of infinitely many solutions as the value of x and equations for y and z in terms of the parameter t. From the original equations, we can see the normal vectors are different for each.
This is the original equation. The normal for this is 2 minus 1, 1, right? The number for this is 1, 1 minus 1. 3 minus 3, 3, which is more or less 1 minus 1, 1. It's not the same as this. So they have different normal. But if actually the planes are coincident, they're going to have the same normal, isn't it? So it means when you take any two planes, they are not coincident. It means they have different normals. Okay? And since we cannot find a solution, then the three planes must have intersected along a line. Do you understand that? They are not coincident, so they are not one after the other. There's no two that obeys that. It's possible you have two coincident and one intersecting, right? Or two coincident and one parallel, right? But if you have two coincident, you should have two equations with the same normal. We don't have that. Because it's possible, anytime you have infinitely many solutions, you always think of, oh, they must be coincident. That's the whole idea here. You have infinitely many solutions. Oh, are they coincident plane? Oh, let's go check the normal. So if you go back to the original equation, actually they have different normal. So for there to be the same infinitely many solution, they are having infinitely many solutions, not because they are on top of each other, but because they intersect a line like that. Sorry, I saw a message maybe from one of you. Oh, our sleepyhead is awake. Our sleepyhead is awake. All right. Do you understand? But because they intersect at a line. Does that make sense? I just want to make sure the conclusion is clear to everyone. You don't need to think of the coincidence until you come here. If you get to this point where you have infinitely many solutions because of the t parameter that was introduced, then go and check. Do they have infinitely many solutions because they are together? Or do they have infinitely many solutions because they interlock and there is a line? Am I making sense? Or there's a line? How do they have a line? Oh, the normal must be different because the normal through this hand is different from the normal through this hand. Am I making sense? But if they are like this, they're going to have the same normal. Understood? So it's possible. Now, if the three planes are coincident, you will get this kind of solution and you will realize that all the three equations have the same normal. It means P1, P2, P3 are together. Does that make sense now? Okay, and this was the
Each plane, and none is a scalar multiple of another. So, no two planes can be coincident. We therefore conclude that we have three distinct planes that intersect in a line.
Okay, so this is something now. So I'm going to send this to you. I'll quickly play the last one. There will be no practice for this session. We will just you will just practice on your own later and watch the video, and all the screenshots will be sent. I can see we are tired. but I want to quickly play example 22, so we don't have to go back to this again, okay? Apologies, it's already 95 minutes. That's why I told you to block off 2 hours, worst case scenario. Okay, guys? So sorry, just a few more minutes and we're out of here, okay? All right, let's do the last one. Please ask question now or later. If you think, oh, I'm too tired now, I couldn't ask question. When you watch the video later, please message me. We have 3 days extra holidays. Let's go.
In this question, we are given a 3x3 system of equations in the variables x, y, and z, but there is also an unknown constant a in one of the equations. We write the system in augmented matrix form using the array of coefficients of the variables, a vertical line for the equals signs, and the array of constants. We can see that we already have a 1 in the top left corner, so we concentrate on getting a triangle of zeros in the bottom left-hand corner. We start with getting zeros in the first column under the 1. Look at the coefficients of x in the first 2 rows. What row operation can we perform on row 2 to make the first element 0? We start with row 2, then subtract 3 times row 1 to generate the new row 2. What row operation can we perform on row 3 to make the first element 0? We start with row 3, then subtract 5 times row 1 to generate the new row 3. Row 2 now starts with a 0. We look to make the second element 1. We multiply row 2 by -1 over 4 to give us the new row 2. We need a complete triangle of zeros in the bottom left-hand corner. So, we need to perform another row operation on row 3. Row 2 has the first element 0, so this is the other row we need to use in our row operation. We start with row 3, then subtract row 2 to generate the new row 3. The augmented matrix is now in row echelon form. Look at the last row. It reads 0x plus 0y plus 0z equals a minus 9, or in other words, 0 equals a minus 9. So, in part B, if a takes any value other than 9, the system is inconsistent and there are no solutions. From the original equations, we can see the normal vectors are different for each plane, and none is a scalar multiple of another. No 2 of the planes are parallel, so we conclude that the line of intersection of any 2 planes is parallel to the third plane. In part C, if a takes the value 9, row 3 is all.
You guys understand the B? Anybody has question with B? Is it clear? Please say something. Is it clear? Give me some facial gesture or give me something like that. Karen? Karen is getting distracted. Is it clear? No.
Yes. Sorry.
I'm sorry, I know you're all tired, but I don't want to go back to this. You know, we have a lot of things to do. That's why I'm rushing this. But I still need to know if that B is clear or not. So tell me something if you understand B part or not.
Yeah.
Understand?
Yeah.
Okay, let's move on.
All zeros, and there are infinitely many solutions. Suppose we let z be the parameter t, then substitute it into row 2. We rearrange so y is the subject. We now substitute for both y and z in row 1. We expand the brackets and collect like terms, then rearrange the equation to make x the subject. We can now write the set of infinitely many solutions as a set of parametric equations for x, y, and z in terms of the parameter t. From the original equations, we can see the normal vectors are different for each plane, and none is a scalar multiple of another. So, no two planes can be coincident. We therefore conclude that we have three distinct planes that intersect in a line.
That's kind of similar to the other one, right? Not exactly the same, but similar. So all this will be shared with you. Sorry for keeping you for this long. I know we are tired. Get why is inconsistent with B, but after when everyone. Okay, Mr. Chang, that's no problem. If there is no question, then I can stop the meeting now. Is that okay? So one thing I will also do is go to your chapter 11 and take a screenshot of things to remember. While you can also go to the YouTube channel where we have posted the video of the class by then and review. But first thing first, do not open this stuff for the next 2 hours. Rest first. Otherwise, we've been having so many new stuff for the past maybe 1.5 hours. So the last thing you want is to continue. Okay? Get some break, go out, eat some food, sleep if you must. So maybe later in the evening, you can even start watching the video all over again. Then it will be like you are hearing this thing for the second time. Yes, exactly. Sleep helps. Get a nap. Yes. Nakita, get a nap because I don't trust you. She doesn't sleep. Get a nap this time. Okay? So in few hours time, wake up, review it, and get in touch with me. And Mr. Cheng, same goes with you. Okay? Your inconsistency, whatever, don't think about it now. Everybody do something fun you like to do. Walk around, watch movies, sleep, talk to mommy, whatever you do. Okay? Play with your cat and that too. Drink some coffee, but please rest. That's the whole thing I'm trying to say. All right? In a few hours time, I'm here. Send me a message. You can we can have a private Zoom session if you need quick explanation for something. All right? And then we can get through with this weekend. All right. Thank you very much for your patience and time. I'll see you on Monday, and maybe I'll talk to some of you over the weekend. Bye.